In this tutorial, we will be creating water mixing effect by using different density and color values. First of all, we need to create an arbitrary geometry that will be used as a fluid source. We can change its scale and position by utilizing transform node. Hold down the Alt key in order to create another duplicate of this node and change its settings to your liking. We can union this to geometry by utilizing merge node. Now we need to turn these objects into the group of particles by connecting both of them to the points from volume node. We are able to randomize their position by increasing the value of jitter scale. The number of particles can be increased by decreasing point separation, but we will leave this value to its default state in order to create dependency with the same parameter in the dynamics network. We can take advantage of the color node in order to colorize these points with complementary colors. Next, we have to create density attribute that subsequently will be used for the mixing effect. Give it an appropriate name and specify different values for both of these particles. Now our fluid source is finished, and we are able to store these groups into the null object. In the second part of this tutorial, we will be working with dynamics network. First of all, we have to define what kind of solvers will be used in our simulations. We will start with the flip solver that will simulate fluid effects, and also we have to transfer attributes of the first object into another one by utilizing SOP solver. We are able to union multiple solvers by applying an appropriate node. Next, we have to create the flip object and connect it to the first input of our multi-solver. As you can see, it creates its own fluid source that is represented as a bunch of spheres. We need to delete it from the SOP path in order to specify our own emitter by utilizing source volume node. Change its initialized type to source flip and add previously created flip source to the source path. Currently, our particle guides are represented as large spheres. We can change its visualization type and color from the flip object. As I mentioned earlier, we will be using particle separation values from the dynamics network. You can simply copy this parameter and paste it to the particle source. For the sake of simplicity, you can use the same values in order to scale down our base geometry. This will drastically improve the speed of our simulation. Now it's time to match the size of our fluid source with an overall scale of the fluid container and close its boundaries from the flip object. We need to apply gravity force in order to add some motion to these particles. If you will play the animation, you will notice that the fluid emitter generates new particles on every frame. This is because our source volume is constantly active. Go to frame 19, hold down the Alt key, and click on Activation Value in order to create a keyframe. Now go to the next frame, decrease this value down to 0, and create yet another keyframe. This specifies that the emitter will take place only during the first 20 frames. As you can see, previously defined density attribute has no influence over the simulation. We have to activate this option from the density section of our flip solver. You may notice that some of these particles are dying under certain circumstances. This is because the particle motion has enabled reseeding option. You can simply increase the value of death threshold in order to prevent our fluid from losing particles. Now it is time to transfer attributes of the first object into another one. Create the attribute transfer node and connect it with our DOP geometry. We have to use color and density attributes and increase max sample count in order to emphasize blending effect between these values, and since our particles are very small objects, we need to decrease the distance threshold in order to get more appropriate results. In the final part of this tutorial, we will retrieve information from our particles by utilizing .io node. Drag and drop .net1 into the DOP network field and use the flip object as the DOP node. Increase the number of fields up to 1 in order to import previously created particles into the SOP network. We can easily convert these particles into the VDB object by utilizing VDB from particle fluid. You already should be familiar with particle separation. Here you can pass here the same value that we have used previously. Voxel size defines the quality of our volume. Decrease this value in order to get an acceptable result. Influence scale defines the distance between particles interaction. We can decrease this value in order to expose more details in our fluid. Droplet scale is self-explanatory. It simply specifies the size of individual particle. We can quickly convert this volume into a polygonal geometry by utilizing Convert VDB node. Simply change its convert type to polygons in order to get desired result. We need to transfer our previously generated colors to this newly created geometry by applying attribute transfer node. If you look closer, you'll notice that the transition of these colors results in jagged edges. This problem can be easily solved by increasing max sample count that will efficiently blur this transition. Now we are able to render this animation in the flipbook in order to see the final result in real time.